Hello, this is Mr. Pruitt, and today I'm finishing up the third part of our three-part series on kinematic graphs by talking about the acceleration versus time graph. So, to review, remember that acceleration is the rate at which speed or direction of an object is changing. So, when we look at something like a roller coaster, there's lots of changes in direction, different changes in speed because of the hills and the loops in it, and we see lots and lots of different types of acceleration here. Now remember that acceleration occurs when an object slows down, and we say that's in the negative direction, or when it speeds up, and we say that that's in a positive direction, or it could just remain the same speed but change direction, maybe turn to a different angle or reverse or something like that. Now remember that acceleration can be found on the velocity versus time graph that we looked at in the last lesson by just calculating the slope of the line segments. So if I wanted to know the acceleration during this part of the trip, I could look at the slope of this line segment that's in the green, and I would know its acceleration during that time. Also remember that even though we can't calculate it algebraically, that we can't use algebra to calculate it, that the shape of the position versus time graph at least gives us an indication of whether or not the object is accelerating. So that when we see a curved graph like this, we know we can look at it a curved position versus time. We can look at it and say, well, okay, I know that this object is accelerating because the velocity is changing at an exponential rate. All right, so let's start with just the basics of the graph. This is an acceleration versus time graph. Acceleration is over here on the y-axis, and time is over here on the x-axis. And what the acceleration versus time graph does is it plots the rate of change in the object's speed or direction versus some amount of elapsed time. So each one of these lines basically reflect some elapsed time that shows some constant level of acceleration. Okay, and they change. I mean, they change. They change fairly. It looks like they change fairly rapidly. But what you would consider is that if this were the velocity versus time graph, this would just be changes in slope. Like here would be this would be something with maybe a positive slope, and then it goes negative for a few minutes, for a few seconds, and then it goes back to a steep positive or something like that. And it's just reflected as these horizontal lines. Now, generally, these graphs reflect the rate of acceleration during different intervals on the velocity versus time graph. Now, normally, acceleration versus time appears as a set of horizontal lines. And this is in this class. This is the type of acceleration versus time graph you will see always in this class. But it's important to know that these could be sloped lines. Okay, and if that was happening, uh, then it would look a little bit different from that. Uh, what you really need to get out of this though is that changes in acceleration in this graph, it's a funny looking graph. That every time we have a change in acceleration, it looks like there's some kind of a drop off or maybe a bounce upward of this, and they're not. It looks like they might be instantaneous by doing that, but probably in real life they're not. It's probably more of a gradual looking thing. But since this is kind of an average or a constant acceleration between two periods of time, uh, it generally comes out looking like there's these abrupt changes. All right, so the first thing when we're looking at acceleration versus time graphs that we really need to look at is the quadrant that things are falling in. And the quadrant lets you know the direction of the acceleration. Okay, so if it's occurring in quadrant one, like the one circled in blue here, then the object is accelerating in the positive direction. That probably means that it's speeding up. or turning in that positive direction. If it shows up in quadrant 4, like the one that's in green down here, the object is accelerating in the negative direction. It means it's probably slowing down, or maybe it's making a turn toward whatever direction we've decided is a negative direction. And then if the curve appears on the x-axis, like the one in red, then this object is maintaining constant speed, because at this point the acceleration is 0. And when acceleration is 0, then we know that it's going the same speed all the time. The next thing that we would look at on this graph is just the line segments themselves. And each one of these line segments represents some period of constant acceleration. So when you look at it, generally the slope of these line segments are going to be 0, which would indicate a constant rate of acceleration. So for instance, this line segment right here at negative 1.0 shows me that the acceleration between 6 and 8 seconds was negative 1, or that it was slowing down or turning into that negative direction. Now, a minute ago I said that you could maybe have sloped lines on these. And so in some very specific cases, like maybe if we were looking at free fall with air resistance, you might see a sloped line. And that non-zero slope would represent some type of exponential rate of change, some type of changing rate of acceleration. In this class, you probably won't see anything like that, but it is something that you should keep in mind for future classes. All right, the only other part of this graph that really has any importance to us is the area under or over the graph. Remember that the area under the graph is we define as basically the area between the graph line or the curve and the x-axis. So this area in blue would be a good example of the area under the graph. If we were talking about the area over the graph, we might look at this area between the x-axis and the graph line that's in quadrant 4. All right. Now, the only thing that this represents is instantaneous velocity of the object. So, if I wanted to calculate how fast this was going at exactly 2 seconds, I would just calculate the area here that's underneath the graph, and that area would be its exact speed at that amount of time. I hope this was helpful for you, and I hope that you've learned something from the past three lessons. Please let me know. Give me some feedback if you have a chance. Thanks. Bye.